Yeah, hello everybody. We are at the point that we yesterday started with the first example of the hypothesis testing. And what have we done? Well, we talked about these pictures that from our estimation we calculate a so-called test statistic, and from the assumptions we made about the normal distribution of the arrows and the independence of the arrows and the independence of the input variables, so that my X value, so that my data set is randomly chosen and that every single variable is independent from the other variable, that with these assumptions we could then deduce the distribution of our test statistics, and then we could formulate our significance value level. And if we, for example, say that we want to make only an alpha error with 5%, then if we have only a one-sided test, we calculate the value, so-called theoretical value, from our given distribution, and then this part here, this would be the interval where we then could reject the null hypothesis. And in general, the null hypothesis is what we want to reject. We formulate it quite often as, well, we assume that nothing has changed compared to the original situation. And this would mean that if we have chosen alpha equals 5%, that the probability mass is here 5%, though the area below the density function is 5%, or in the other direction. This area has to be 5%, or what we also are quite often doing is a two-sided test, especially in the linear regression. Then the null hypothesis is quite often that our parameter beta is 0 or not, and then the sum of the left and the right side of the distribution has to be together the significance level. So in case of alpha is 5%, both areas has to be 2.5%. Yeah, and with this, yesterday we went to our example regression that in general, so to speak, we want to test our correlation coefficient. And if we have calculated our correlation coefficient R, or the coefficient of determination, just the square of the correlation coefficient, then it is possible to show that the test statistics R squared over K, number of parameters, over 1 minus R over N minus K minus 1, that this test statistic is F distributed, and I showed you it is a quite complicated function, this F function, but with a software package we just can implement this function and then can directly calculate the theoretical value. And with this, we went to our example. Again, let's go to it. Our linear regression. It was this example where we had 3 input variables which should explain our output variable, the number of sales. And we calculated an R squared, I think this was, yeah, here it is, of 0.72. And then we ask, given our sample set and calculating these R squared of 0.72, if we want to make, in our case, just 10%, only with 10% an error, we will compare this to the null hypothesis that although we find an R squared of 0.70 of 0.72, with which probability is this distinguishing from R squared equals 0. And this meant then, if we choose alpha equals 10%, we take our F distribution. This is depending on the 2 parameters, k and n minus k minus 1. This is the blue line. Then we calculated where do we find our F value from these theoretical distribution, the blue line, for a significance level of 10%. And this we find then to be 5.34. I showed you that this is, of course, implemented in Excel, or one could look it up in tables. This still have to do many students. I don't know why, because I'm a fan of applying all the helpful software we have. And then, since we calculated R squared is 0.72, we know that we have 3 parameters. We know that our sample set data points, we have 8 data points. We just can plug in these numbers. This we did here. And then we obtained from our empirical data set an F value of 3.4286. Well, and this data point is between within the interval of these 90% where we cannot reject our null hypothesis that R squared is different from 0. So again, from a purely descriptive interpretation, we had said, well, with our model, we can explain 72% of the dependence between our X parameters and our output, the sales Y. But then from a statistical interpretation, we cannot say that even this linear dependence between X and Y exists with a probability error of 10%. Well, and this, I think, is a really important information if you make your management decisions. because of course I give you any data and you always can run a linear regression. But then you have to be careful to interpret the outcome of your linear regression, because in this case, if the managing board of your company says, well, this is quite a risk if we make an error of 10%, that there is even no linear dependence between my x variables and my y variables, then I couldn't hardly take these r squared of 0.72. Okay, but then also we are not only interested in the question, is there only these, where is it, my example? Here, is there a general linear dependence? But we, of course, are also directly interested in the question, how reliable are my fitted parameters beta itself? And this we will do now in the next step. And now, in general, our hypothesis would be that not simultaneously all betas are zero, and we are testing for the case, is there, given a special probability, one parameter different from zero? Now we ask in concrete for one parameter beta as a null hypothesis to be zero, and the alternative hypothesis is that this specific parameter, given for example I equals 2, then it is the parameter of if we open a store or not. Is this different from zero? And again, we choose our significance value level, and then with the opposite probability, 1 minus alpha, we are not rejecting our null hypothesis. And now our test statistic is our estimated parameter. This was our, for this beta roughly minus 3. And so to speak, we normalize it via its standard error. And from this, we know that this is t distributed, also a symmetric distribution in the neighborhood of the normal distribution. Well, if we choose as null hypothesis beta is 0, then we would set this just to 0. Well, and also this distribution depends on the degrees on freedom. So then let's use also our example, and there we choose our significance level, and if we use alpha equals 5%, then of course we have to be careful that these areas here and this area here is 2.5%, because we have a two-sided test. The number of degrees of freedom is again n minus k minus 1. So we have 4, and so then we have to take the t-distribution for the parameter 4. And why I don't have the table here, then let's calculate this within Excel again. Because of course also the t-distribution is tabulated here. And of course, again, we want to calculate it inversely. Given our t-distribution, we want the x value corresponding to it, so inverse. And our probability is now, since we have to calculate the number at both sides with probability mass 2.5%, we need here 0.975, and the number of degrees of freedom was 4. And oh, did I it wrong? Actually, yes. 7.5. Then I have to change these numbers here. This is then not minus 2.17, but 7.7 I made here. Just the mistake that I didn't choose the 2.5. And here I choose, oh, this was the reason. Here, sorry, because I just chose here alpha is 10%, and here I wrote alpha t 95%. So this has to be then 90. And let's write down then t 97.5% of 4 equals 2.77. Well, and now we have to calculate our empirical t-value, and the empirical t-value is our beta hat over S beta I, the standard error. And in our example, we had, I haven't calculated the standard error, why not? So beta 0, this is all these numbers. Let's move this up here. So here I have my beta values, but I need also the standard errors. Well, then I directly calculate it. We will do it also later on in one exercise. So let me just take the data, going in here. No, again. And as I showed you, we have here the direct possibility, RGP function. Then we need the Y input vector and then the X input vector. And then we have also to add true, true in order to obtain all our regression parameters. And this is for beta 3, 2, 1, and 0. 0, 1, and 2. And the second line are the standard arrows. So then we can skip this and using now this one. So what we then have to calculate is T empirical for beta 3 is minus 2.990. I have to, this is roughly a 3. So it is minus 3 over this as standard error, 3.46. T empirical of beta 2 is 0.46 over 0.24. T empirical of beta 1 is 0.43 over 0.7, and T empirical of beta 2 is 7.42 over 6.31. Well, since I'm always want, oh, here I have it, sorry. There it is, but anyhow, let's calculate our t values. So t3, t2, t1, and t0. This is beta minus 3 over 3.45. Let's take this and put it also where I do have some space left. Let's move it here. So we obtain minus 8.7, 1.95, 0.61, and 1.18. So let's now take some different colors for, oh, this is beta 0. Oop, beta 0. So then let's start with beta 0. In this case, we have 1.18, so we are somewhere here. T0, then for T1, let's take blue, 0.62. T1, 0.62, T0 was 1.18. Oh, this has now to be 95% also. Sorry. Because everything I changed to alpha equals 5%. So then also T2 is 1.95. There we are almost. And T3 is minus, what else? Let's take yellow, minus 808.7. So we are somewhere around here. T3 minus 0.87. Well, and then we see that all empirical t values are within the interval where we given alpha equals 5%, H0 is not rejected. So, given our data set, then means also, although we have descriptively found our dependence between the specific x values and the sales representing the output y, we cannot say that for a given probability of 5% that these values really differ from 0. Well, this result is not that surprising, since within the former hypothesis test, we found that we in general, given even a significance level of 10%, we cannot say that R squared is differing from 0. But you have to keep in mind, it has not always to be the case that if we are not rejecting the null hypothesis in the F-test for R squared, that this also directly always means that given the same error probability, we are also reject the null hypothesis that every specific beta value is also not differing from 0. And this maybe you can also see here that for the second parameter, we have already a t-value which is quite in the neighborhood of the critical theoretical value. Okay, I overlooked, sorry, the slide here where we should have done our regressions. But I see here that this is another regression. Well, in this case, as an exercise, we can also calculate together all the critical and empirical values for this case. And hopefully now you can help me. So if we make again the null hypothesis that beta I is 0, then H1 would be beta I is not equal to 0. Then at first we have to calculate the theoretical value T of 97.5% with n minus k minus 1. We suppose again, given n minus k minus 1 equals 4. This we again take from our value here. This was again our 2.78. And now given these values for the standard error and our betas. Now you should help me. What do I have to calculate for the first parameter beta 1? If this is beta and this is the standard error, the empirical value. Any idea? Well, this is defined as beta 0 over S beta 0. So 10.669 over 7.579. T1 is then 1.484 over 0.911. T2 is 0.718 over 0.199, and T3 is 9.008 over 4.150. Can I use this? Hopefully, no. So I have to type this in. So T0 is 10.669 over 7.579. T1 1.484 over 0.911. There I need an equality sign. T2 equals 0.718 over 0.199, and T3 is 9.008 over 4.15. So we have 1.41, 1.63, 3.61, and 2.17. Well, and now how to interpret it? Well, again, let's look at the t-distribution. This looks somehow symmetrically. Again, we have our critical value 2.78. This means, again, this would be the both intervals where we reject H0 with a probability mass of 2.5%. And then let's do it again with different colors. Here we have 1.41. This would be somewhere here. T0. 1.63 for T1. Blue one. 3.61 somewhere here for T2, and in the end 2.17 somewhere here for T3. And thus for a significance level of alpha equals 5% for beta 0, beta 1, and beta 3, we cannot reject H0. So these parameters do not significantly differ for alpha equals 5% from 0. Only for beta 2. In example, we have 3.61 is larger than 2.78. We can reject H0 for alpha 5%. So taking this example here, where we calculated other beta values, given these beta values and given these standard errors, only the second parameter differs significantly from 0. Okay. Also, I can show you, if you do not want to use a software package, this is then some of these empirical tables you find for the t-distribution. So this is the number of degrees of freedom. And this here is then 1 minus alpha, with alpha the significance level. And so then we have to look up here these number by hand. And the F distribution I already showed you. Here you have these two parameters which we have already looked at. Okay, that much. And now, as I said yesterday, I want to start to do some exercises about linear regression with you. Then let's start. Another screen. And not here. So exercise 2, number 1. Given the housing market, actually right now quite interesting. We have taken a sample of 26 flats, and then we got some data, and from this data we want to calculate the linear regression for the two variables, size and the rental of this flat. So we will then, of course, formulate it in this way that we say the rental is depending on the size G of the flat. So rental should be Y, the dependent variable, and size should be the independent variable. And we know the covariance, the standard error of the rental and the standard error of the size, and we know also the expected values of both. Variables. Well, in order to calculate the regression line, what do we need? We just need our formulas. How does the regression line depends on the expected value and the variance and the covariance. And this we had in this case here, that parameter B is just the covariance over the variance. So A, parameter B, so the slope of our regression line would be the covariance of xy over the variance of x. So what do I have then to calculate? Please help me. So where's my chat? Oh, where is it? Not there. There it is. What is the covariance and what is the variance of x? Well, we have defined rental is y and size should be x. You still hear me? Well, the covariance is given by 5,760. Size is x, so 21.9. And since this is the standard error, the variance is just the square of this. So let's calculate this. 2 B is then 576 0 over 2.129.1 squared is roughly 12.01. How do I obtain the cut of the vertical axis? Well, this I get from the fact that also the average values, oops, since nobody is in today, my Beamer screen is vanishing. Well, and the average values we have empirically also given by mu m and mu b. So in general, we know that y bar is also a plus bx bar. So we obtain a in general is y bar minus bx bar. Feeding this in, we obtain this is y. The rental is roughly then mu m equals 1100, and this is mu g equals 80. And then we have 1100 minus b we have here, 12.01 times 80. And this is roughly then A, we need 1100 minus B times 80, 139.22. 139.22. So the regression line is then given by y equals 139.22 plus 12.01 times x. What is then the marginal and average price per square meters? Well, for this, we have just to divide our two average values equals mu m over mu g is 1100 over 80, and this is over 80, 13.75, and the marginal price per square meters. What is this? Well, this is the reason why we are doing all this, because from our analysis, we want to have an idea if I find not only a flat with a size, with an average size, I want from my regression to have an idea. For example, if I have a flat of 200 square meters, what would it be? So I want to know marginal price. What is the additional rental for the next square meter in size of my flat? Well, and this is of course nothing else than the first derivative of my dependence between the price and the size of my flat. So this equals y prime x, or dy with respect to the x, and this is of course nothing else than 12.18, just our parameter of the slope. And the last one, estimate the rental of a flat with a size 100 square meters. This is then just y of x equals 100. And what do I have to do here? 130, 40. This seems quite good. Can you also, give me a hint how you have calculated it? Yes, just 13920 plus 1201 times 100. So I put it in that y of x equals 100 is a plus b times 100, 1340.2. Okay, another 15 minutes, so we can also start with the next exercise. Where do I have it? There it is. Where's my cutting tool? There. So what we should do here, now we have a brewery where we have the input costs and the output of hectoliter. Well, this is the data from 1 year, and we want what we want to do now is, given this data, to explain the output, or to explain the cost function from the output. And this, I think, you have quite often done in other courses. We are looking for C of y equals C0 plus Cy of y. And this is nothing else than our fixed costs, and these are our variable costs. And in our case, we are assuming a linear dependence. So this translates then in the 0 plus Cy with a fixed number times y. And then, of course, also we can again interpret this as the marginal costs. Or this would be then, and please not be puzzled, this we quite often do, that we just give our parameters some names via the letters, compare this with our general dependence between y and x in the regression line. So in our case, y would be then our total costs. C, A would be our fixed costs, B our marginal costs, and this would be our output y. So here, be careful that you don't mix up these two y's because they have different meanings. Yeah, now we have to take these data and try to calculate our regression, and this again we will do together within our software package. Let's also again, oops, a bit larger, maybe 150. Did you see anything? So I think I can copy this, or is this possible? This is also what I want always have to somehow try, in which kind of format I obtain the data. And this is a quite nice format, because now I can manipulate this data, go in to data, and then put it into columns. And then what is the spacing is not a tab, but the spacing is one left out sign. And after this, I have my data set. So this was output, and this were costs. Where is it? There. So then, of course, I could it do directly feeding in these numbers just in a diagram. This I have shown you. Then we could click right on this trend line. You don't see it. It is over here. We have already linear, and then we also want to have the formulas. So then we actually already done, but in order that you know what you are doing, we also want to use the formulas, and this you had in your script. Remember it. Let's go again here. So what we need is x times y, and we need x squared. So if this is x and this is y, we need xy and x squared. So multiply this times this, and x squared is this squared. Copying this downward here. What else do we need? We need always the sum of these numbers. So we calculate the sum here. And also we can just copy this to the right. Then we have always the sums of the different colors. This you see if you're clicking into the formulas. Well, and then for B, we need to have the amount of our data set is n. It is 1 year, so n is in our case 12 times the sum of the products minus the sum of the x times sum of y over 12 times the sum over the square root of x minus the sum of x and then squared. So this is then, let's write down here, the number is 12 because we have 1 year, and then it is open brackets 12 times x, y, the sum, minus the sum of x times the sum of y over, again, n times the sum of x squared minus the sum of x squared. 5.04 is surprisingly the same we had here via the diagram. And A, we again obtain via the property that the average values have also to lie on our regression line. So y bar Y bar is nothing else than the sum of all y's divided by the number 12 minus b times x bar. Average of x is the sum of x over the amount of our data set, 3620, and this we have also here. Then let's save it before I forget it. Size. So let's copy all this into, oh, this is the wrong one. There we are. Calculate the cost function via the regression line. This we have done here. Let's put also the diagram. Within here. So here we also have to add this up. This is this was output, and these are the costs. And here B we obtain to 12 times xy 10657,511 minus the product of these two over 12 times x squared 125,95811 minus x in brackets squared is 111,900 squared, and this is 5.04, and A is y bar minus bx bar is then 103,000 over 12 minus 5.04 over 12 equals 3,620.7. Well, the interpretation you find here. So this is A. That we can say. Now we have fixed costs. That the cost independence of output is 3,620.7 plus 5.04 times y. So these are marginal costs, and these are fixed costs. And we should calculate also the correlation, but since I'm running out of time, well, here we have calculated already. So if you do it I would announce that you try it at home within Excel from these data that you can verify this value, and well, D we can already do. This means just C of Y equals 1100, and this is then 362.7 plus 5.04 times 1100. This we can just do here. C of Y equals 1 is then this plus this times 1100. There's 10 missing. 9165.2. 9165.2. Yeah, then do this homework. Well, what else can we do? We can also here hypothesis testing. So test for, let's say, alpha equals 1%, an F-test, and test also for alpha equals 1%, a t-test. This would be for r squared, and t-test for a and b. Let's see if you manage this. Okay, then see you on Monday.